November IMEDS community call. This is Christine Yu from the Reagan-Udall Foundation. Please note that we are keeping this presentation on mute for the audience for the time being in order to cut back on the background noise. We will take everyone off mute at the end so that we can have a short question and answer period. So one quick announcement from IMEDS before the presentation. We will be sending out a survey to our users in the IMEDS lab after this call. The survey will mainly be used to help us assess and improve on the resources and the services we're currently providing in the lab. It will take less than 5 minutes to fill out, so we'd really appreciate it if you could participate. So with us today is Dr. Jinghua He from Merck and Dr. John Duke from the Regenstrief Institute. The title of their presentation is Use of Natural Language Processing in Observational Research. The slides for this presentation were sent out yesterday, and you should also be able to see them on your screen. We'll post a copy of them along with the recording on our website afterwards as well. So Dr. He and Dr. Duke, thanks so much for joining us today, and I'll now turn the presentation over to you.
Thanks, Christine. Can you hear me well?
Yes.
Okay, great. Good morning, everyone. It's a great pleasure for me to be here and co-present with my partner, John Duke from Regenstrief Institute. So this is Jinghua from Merck Pharmacoepidemiology Department, Center for Observation and Real-World Evidence. John, would you like to briefly introduce yourself?
Yes, thank you very much. My name is John Duke. I am a physician and research scientist at the Regenstrief Institute, and I lead our drug safety informatics laboratory there, as well as a partnership between Merck and Regenstrief.
Okay. Thanks, John. So today's presentation will consist of 3 parts. First of all, I'll briefly introduce the partnership between Merck and the Regenstrief, and then I'll pass the control to John, and he will talk about the Regenstrief natural language processing platform. And thirdly, I will talk about a use case of natural language processing technology, which is to identify metastatic melanoma cases in EMR. All right, so Merck and the Regenstrief Institute come into a strategic partnership since 2012. It has been working really well and very successfully in the past 4 years. The mission of this partnership is to improve the health of patients through innovation, data analytics, and research that supports personalized delivery of care. So we have a variety of types of collaboration projects, including research methodology development, observational studies, health IT development, education and training, etc. In the past 5 years, we have finished accomplished over 30 projects, and over 10 projects of those are natural language processing related. And today, we are going to share with you some natural language processing work that we have been working with together. All right, John, I'll pass the control to you from now on.
Thank you very much, Jinghua. So I wanted to introduce a little bit about the Regenstrief natural language processing platform, but more generally about natural language processing in observational research to try to provide a bit of perspective. There's been a lot of talk about NLP. I just came back from the American Medical Informatics Association conference this past week, and you couldn't really go probably 2 rooms without catching an NLP presentation. There's a lot of interest in this space, but I wanted to start really at the fundamentals about why and how we are interested in and engaged in NLP. So the reason for sort of this rising interest in natural language processing is that free text documents, which can be physician notes, path reports, radiology reports, triage notes, etc., have a vast amount of information that's not adequately captured in structured data. I use the term structured data to refer to things like ICD-9 codes, CPC codes, dispensing data, unstructured data referring to free text. It's often quoted 80% of information in healthcare is in unstructured form. think it's hard to get an exact number on that, but I think everyone would agree there is a lot of good information that's been sort of locked away. And there's a number of uses that we can go into, but really ranging from patient care to research, quality, trial recruitment, patient engagement, and so forth. Just to define terms a little bit, so NLP as a formal term, natural language processing, is really a field that combines a few different elements from linguistics, computer science, and artificial intelligence. And a big part of that is what's called natural language understanding, which would be a computer actually being able to understand written text. And that's a pretty tall order for a computer. And a lot of times when you hear the phrase NLP used generally, and how I'll use it today, it's something a little bit more like text mining. It has a very broad definition, which could include understanding the text. It also includes sort of advanced information retrieval mechanisms, finding patients, finding outcomes based on patterns. It also includes value extraction, so finding things that you want from a report, like an ejection fraction, from a echocardiogram report, or a tumor stage from a past report. And then predictive modeling is often wrapped up in there as well. So we're using free text documents to try to predict risk or identify patients with certain characteristics. So you'll hear the term NLP meaning a lot of things, and when you're talking to general researchers, it can be used pretty loosely, and I think that's completely fine. But if you happen to find yourself in a room full of NLP researchers, they may give you kind of a sideways glance if you refer to the non-pure form of NLP. So just wanted to clarify those differences. Clinical documents, of course, you can imagine tons of different types. Again, provider notes, discharge summaries, path reports, radiology reports, laboratory results. While in many forms, and many times structured, there's often, of course, unstructured types such as culture reports and other titers that may be not as easily parsable as pure numbers. At Regenstrief, we've got in total about 130 million documents. We've loaded in a variety, about 20 million provider notes and 25 million radiology reports, just to give you a sense of the kind of counts that we have. More important than the actual number as a pure amount, I'll say that we've actually been capturing documents since the early 1980s as part of a health information exchange at Regenstrief, but we didn't even look at them for about 25 or almost 30 years, and they just sort of sat there. So really the volume at most places is quite high, but how do you use them? And I wanted to describe in general the components of an NLP system that you might commonly find. So there's typically a number of data sources, and so you can see that you can pull in data from EHRs, you can pull in data from administrative claim, but also registries and trial data. All of them can go into a text-based repository because it's a very flexible way to store things. So typically you take all of the data that you have from different sources, you put it into a report repository, which sort of stores the data, and then you have a couple different ways of getting at it, and this is sort of two of the big ones. So one is what's called a report index, and it uses something for high-speed searching called an inverted index, and I'll show you an example here. Anyone who has a Mac computer there knows the little Spotlight button, and what Spotlight does is it creates an index, or what's called an inverted index, of all of the documents in your computer, and it basically says for every word that you have in any document, it says, here's the word, what documents is it in, what positions do I find it in, and it creates this easily accessible index. So when you click the Spotlight button and you search for something, it essentially immediately can find that information. But it churns for quite a bit of time. If you've ever seen your computer just kind of thinking while you're otherwise not doing a lot, it's typically indexing your documents in the background. And so that's how an inverted index works, and that's one of the sort of high-speed aspects of information retrieval, which complements some of the deeper NLP components. The next piece, if you look sort of in the lower right-hand side, is what would be called a pipeline. And pipelines are sort of more of the real, quote-unquote, NLP activity, where you're doing a lot of different processes to try to better understand your data. And so I'll give an example of a few. Here is a sentence up at the top. The patient underwent a CT scan in April, which did not reveal lesions in his liver. And then you have a lot of different activities. So things like tokenization, splitting up words, normalizing is getting the sort of structure. So for example, underwent becomes undergo, lesions become lesion. These are kinds of ways of stemming and making all the words that are sort of part of a family together. You can look at part of speech if you need to. You can match them up with UMLS terms, which is a big dictionary. For example, the SNOMED terms that may fit, or in some cases could be RX norm, could be ICD-9s or other sources. And then depending on your needs, you can break down sentences in more sophisticated ways around nouns and verbs, and essentially understand, for example, here under entity properties in orange, was it negated? So it's a big difference between the patient had a lesion and the patient did not have lesions. And you can see in this case, it says lesion is negated. That means it's no evidence of a lesion. And it was the subject, the patient themselves, was the subject, a family member, etc. And so these kinds of things are part of what these NLP pipelines do. And when you take them together, you have sort of a way to comprehensively look at a lot of elements of your data. And this is just an example of some of the technologies that are pretty standard these days. Hadoop is typically used for storing reports, but they can be stored in other ways. Things like Solr or Elasticsearch are used for fast reporting. And then there's some really nice open source pipeline elements, CTAKes, UEMA pipelines, OpenNLP. These are basically open source processes and infrastructures that are used for NLP frameworks, though it does take some expertise to put them together. So how do we use NLP practically at our institution, our collaborations, and our research? So the number one use is for cohort generation, for finding patients, for example, with conditions that are poorly represented in structured data. So symptom-based conditions is a big one, patients with problems related to sleep, problems related to sort of a review of systems type capture as opposed to a diagnosis that might be put in an ICD-9 code. Finding patients based on radiology or pathology findings. The impressions of those reports are typically locked away. Categorizing disease severity is one. And then, for example, looking at cancer staging again, it's a common use to try to categorize or group patients, but cohorts for trials, for research, is the biggest use case. There are a few other use cases, though, that are worth noting. One is converting unstructured data to structured. So I mentioned ejection fraction, things like mini-mental status exam, Karnofsky scores, which is quality of life score. Even glucose levels turns out to be one that is very useful for NLP. And you may think, well, glucose is probably one of the most common laboratories there is. It seems silly that would be something that you would spend time with NLP. But when you're looking for side effects like hypoglycemia or low blood sugars, those types of things typically occur not when someone's sitting in the doctor's office getting their blood drawn, but it occurs at home and they report to the doctor, yes, I've had some glucometer readings in the 40s, or I had some shakes and I took some orange juice. And those kinds of information pieces, even though they're related to a laboratory like glucose, are actually much more effectively identified using a combined structured and unstructured data approach. We also look at things like sentiment, decision-making. Why did someone discontinue a drug? Why did a patient refuse a drug? What are their thoughts about that? And then clinical trial recruitment is obviously sort of a superset of these things, but processing eligibility criteria and matching patients is a big area of interest for a number of places. Here's an example of some NLP projects we've done recently, looking at patients with metastatic melanoma, which Jinghua will describe further. Identifying atypical hip fractures, hypoglycemic events I mentioned, patients with family history of certain cancers, quality of life status after cancer treatment, staging for tumors, determining lack of drug efficacy for insomnia, reasons for refusal of osteoporosis, identifying patients with peripheral arterial disease. You can see it's a pretty diverse set of things that you might tackle, and it reflects the fact, as you would with any set of data in healthcare, there's a lot of different types of problems that you can address, and NLP and unstructured data just adds to the breadth of things that you can do. I did want to go through, in sort of a stepwise approach, how we think about doing NLP-based research, just to give you kind of a framing. And this does, of course, require some access to unstructured data In some cases, that's available if you're at a health system. But even if you're not, if you have clinical trial data from your own research, if you have data that is been collected looking at molecules, data that has been collected looking at the usage of things, even administrative and data can be applied in the same way. And this is the pathway that you typically follow. One is to define a question, to build an initial phenotype or a definition for that group, to extract and process the documents, to validate and iterate, and then apply to your particular use case. And I'll walk through these one by one. So to define the question, here's a couple examples of what might be a regular person giving a human, description of what they want to do. So I'd like to better understand sleep quality. It's buried in the notes. So please help me find all patients with evidence of sleeping problems. Another example, someone doing a study on interstitial lung disease, and they want to have an automatic maintenance of a list of all patients who have radiologic evidence of interstitial lung disease or pulmonary fibrosis. And so both of these are just someone's describing something, and you have to begin breaking it down into ways that can be computed. And that's the same, of course, whether you're doing structured or unstructured research. So the first thing we do is we consider what structured criteria do we want. So are there certain demographics or ICD-9 codes or SNOMED codes or CPT codes that we want to form the basis or the beginning of our search strategy? And sometimes there are, or sometimes you want to take just the full set of patients that you have available. The next step is really to get expert input, or what might be called a heuristic approach, where you talk to experts and say, well, what sort of terms and phrases should we be thinking about? What types of reports should we be looking at? MRI reports, CT reports, cardiologist notes, oncologist notes. What is relevant? Looking at medications or procedures, beginning to get that sort of sense from experts of how you might approach it. That can be complemented by the use of ontologies. So ontologies, or sort of these terminology hierarchies, SNOMED or MEDRA and other sources, can be used to find synonyms, related terms, and we can also process lexical variants, so that if I put something like sleep, I can also get slept and sleeping and so forth without having to kind of manually do all of that. The final step of the preparation is discovery. So let me give you a couple examples. Sorry, here. This is an example of MEDRA term for insomnia. So you can see that I put in the term insomnia. This gives me counts of in our institution, different appearance of frequency of the terms. And then you can see words like sleeplessness, sleep loss, transient insomnia, awakening early, etc. Depending on what you want, you can select representative phrases. And this would be a similar example for interstitial lung disease, which I'll skip here. The discovery step is an important step. That says, well, we've taken expert input and we've looked at the terminologies and such, but we want to understand what can we learn from our own data to inform that. So in this case, we might use what's called a silver standard structured phenotype. So we're going to say, I'm going to take the diagnosis, for example, of lung cancer, and I'm going to look at those documents and do certain analyses to find terms that I might not have thought of to put in my original definition. So here's an example where I've taken patients with an ICD-9 code of lung cancer for that day, and I pull out their notes, and I do something called a trigram, which pulls sets of terms from the all of these 150,000 notes and shows me what the most common phrases are. And I can discover things that are both, I might have suspected, but also things I might not have realized. So ALK fusion is a gene that's often looked at in lung cancer, and it's something that you might not have thought, well, that's really indicative of lung cancer for my definition, but in fact, it's highly specific, and typically when it's mentioned, it refers to a patient who fits in this category. So you can do discovery using things like engrams and review of documents that fit a quote-unquote silver standard, which might be based on just pure diagnostic codes. The other thing you have to look out for is misspelling. So if you're saying, let me look at some drugs that fit this condition, like tamoxifen for breast cancer, it'd be nice to just type in tamoxifen and off you go. But it turns out that doctors and everyone else documenting can make quite a few misspellings. You can see here examples of tamoxifen, 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 etc., that you would miss if you just took tamoxifen straight away. So being able to capture these variants is an important part and value of the NLP platform that we apply. And here's the same example, insomnia, also seemingly a relatively easy word to spell perhaps, but a lot of different spellings and inclusions of different letters and E and H's and so forth. So once you've kind of gone through and thought about the question, you can begin setting up an initial phenotype. You might do a simple search using different phrases, using term distances and things like that. Whatever it may be, you begin with a simple search in our environment where we just get a quick look in just a few seconds. What documents and patients and document types match this group that I've defined? And this is sort of what you would call a first pass. It's kind of a poor man's search. You've done a lot of work, but it's just an initial look. And so in our environment, we run these searches. We get some kind of instant breakdown, demographics, look at report types, et cetera, that we can use. And that's a great starting place. But then what you want to do is take these documents of all these different types, and you can see your progress notes, discharge summaries, et cetera. You can actually do some manual checks looking at the documents, and I've de-identified these, but manual checks looking at these documents and saying, am I getting back what I expected? And it's important to do a look here. We'll do more formal validation in a moment, but the first step is just, okay, yeah, does this look like what I was searching for? And say, okay, yes, it looks like this is a fit for the definition that I had in mind. Now let's go a little bit deeper into the analysis. And by going more deeply in, we can, for example, identify sections of the reports, things like negation or context. Is it a probable event? Is it a historical event? Is it a marker of a family history? Or can I pull out particular values that I'm interested in? So these deeper analyses typically take a bit longer, maybe 10 minutes. For a few hundred documents, might just take a couple minutes. For 100,000, it might take 15 or 20 minutes. But these basically can run and pull out more detailed data. So to show you some examples, I'm in this case looking for peripheral vascular disease, claudication, and markers like that. And I can see that some of them are negated, no palpitations. Others may be affirmed. So there's, we have conditions suggestive of lower claudication, et cetera. So this negation factor is very important and is a critical part of defining those groups. We similarly can have things that are possible. So a lot of times doctors will write, rule out claudication, rule out vascular disease, et cetera, and that can be captured and stored as a possible event. And you can say, well, in my study, I don't want to consider possible events, or I do want to consider possible events because I want to capture a broader net, depending on your use case. Here's a situation where, for the same topic, claudication, I'm looking at history of present illness. And the history of present illness in this section tells me, well, this is what the patient's complaining of or what the physician is describing. And it has a bit of a different implication in the HPI than it might have, for example, if it was in the plan, where I see that the doctor is referring to claudication as something that's going to be part of their descriptive plan. You might say, well, if it makes it into the plan, then I think it's at a higher level of confidence than if it's a patient complaint, which the physician has not yet sort of ruled on their evaluation. And so the section can be very helpful in those sorts of ways. Another thing you might want to look at is family history. And so in this case, we have a parser that identifies who the individual is, what degree relative, what the condition is. And so it can see here, father died of colon cancer, brother was diagnosed with colon cancer, et cetera. And you can take that information and then apply it if you're looking at certain risk models, you're looking at preventive screening. And there's an example down here where there's actually a mistake where the doctor had misspelled brother as brother with a P, and the system conflated and thought, okay, the father had colon cancer, where in fact the father had died of lung cancer, and it was the brother. So there are still places where you can, of course, find errors, but the performance is extremely good for identifying these types of conditions, whether it's family history in a dedicated section or whether it's just described in part of the patient's past medical history. Another use case, as I mentioned, was identifying or pulling out formal values. So Karnofsky scores or ECOG scores are often used to look at cancer performance status or performance status of individuals after cancer treatment. And so what you can see here is that we're essentially pulling out these values for the Karnofsky scores, and it can be tricky sometimes because you can have a mix of blood pressure and heart rate and other things like that. You want to be able to identify these terms. People often sometimes make misspellings, etc., as well in these contexts. But here's an example of pulling out particular scores for a given condition. Sorry if this is a bit hard to see, but what this is once I've created this sort of analysis, I can set criteria for what I want to include in my cohort. So include only affirmed cases or negated, include family history or exclude family history. I only want present mentions. I only want things that happen to the patient versus happen to someone else. So in our platform, we can sort of define, here are the elements that we want to include, here's what we want to exclude, and then it produces a cohort that matches more deeply what we're looking for. Now, in order to make NLP both valuable within the research that you're doing, but also trusted when you go out to do publication or present these to external stakeholders, you need to evaluate against some type of gold standard to establish confidence or at least the level of performance of your analysis. And so we typically do some manual annotation, often in an iterative fashion. So in our environment, we have an annotation platform that we kind of combine, which allows you to say, for example, if I found 5,000 patients that match my cohort, I can randomly assign 500 of them to a set of reviewers to answer a set of questions regarding those findings, and then help from those numbers, we can determine the performance of the algorithm. And so typically, and here's one where I'm looking at NYHA class heart failure. Typically, when I'm looking at performance, I'm looking at things like recall and precision. Recall typically would be sensitivity. Precision is a little more like specificity related to positive predictive value. You often see a term called F-measure used in NLP processes, and that basically is the harmonic mean of precision and recall. But basically, you're looking for numbers in the upper 90s. Depending, though, on your use case, you may be able to forgive either the sensitivity, the recall, or the specificity. Most NLP activities, people, for example, say, well, we want really good precision. We want to be sure that everything we pull is accurate. We're willing to miss some cases. But in other contexts, for example, when we're helping people reduce the amount of manual chart review that they're doing, then they're very interested in saying, well, we want the sensitivity to be good because even if you've got some false positives, we have reviewers. We just want reviewers to be spending less time looking at thousands of documents and instead look at hundreds of documents. That would save us a lot of time. So depending on the use case, we tune that. In our environment, we allow for the storing and providing context around a given query or analysis. So once you've gotten your query just right through a series of iterations, you can store it and you can share it with colleagues so other people can reuse that search strategy to find patients that they may have in a similar context in the future, or they can modify your query for a different use case that's related. And those are then available to users, and so they can look at, okay, what was the performance of this particular algorithm, and what underlying studies or references do you have that support your use of this particular query. So we try to make that as easy as possible. Finally, when you've completed your phenotype, your definition, through a series of iterative rounds of processing, one is you may want to write data back to the warehouse. So you may want to say, well, that took a lot of work to find those patients with insomnia or interstitial lung disease. I want to store a structured data point back in the warehouse. So yes, I do the NLP and maybe I run it once a week, maybe I run it on demand, but I'm going to put a code, like a LOINC code, back into the repository so then I can just search for it in a good old-fashioned way. But you might have other things you want to do, such as data analytics around epidemiology or observational research. You may want to do some type of real-time surveillance, trial recruitment, or prospective-looking studies. Or you may want to do clinical decision support, where you feed it back for patient care or quality metrics at an organizational level. So all of these are very common and useful applications of NLP downstream. So what sort of benefits have we seen from our work? Well, we've seen really fantastic benefits across all of the domains that we've applied. So the study I was mentioning before with peripheral arterial disease, I'm looking for patients using unstructured text versus structured. We saw a fourfold increase with a 98% positive predictive value, increasing our potential research cohort from 10,000 patients to 43,000 patients. Hypoglycemia using the unstructured data increases about 21% from 9,000 to 11,000 patients, also with very high positive predictive value. Looking at things like family history, breast cancer, lung cancer, colon cancer, we also saw very high levels in terms of the positive predictive value. And essentially, we had almost no data on family history in structured form, or a very small amount prior to this, and generated data on thousands of patients using NLP. So something that really wasn't available before became available after. So I hope this gives you a little bit of perspective on how we're using NLP. I want to give special thanks to the team and many individuals, both at Merck and at Regenstrief, who were involved in expanding and developing and doing research on this platform. And I'm now going to turn it over to Jinghua to provide a deeper dive into one of those research projects.
Thank you, John. Okay, so I'm giving you an example of the application of NLP for a study we did last year, which is to compare the structured data query method versus natural language processing to identify metastatic melanoma cases from electronic health records. So John talked a lot about the natural language processing, which is a great tool. It has many potential applications. But as an epidemiologist, what I most care about is that NLP can serve as a novel measurement tool that allow us to extract information that are not routinely available in large structured data like claims or EMR data. And by saying this is a measurement tool, then we truly care about the validity of this tool. It's just like when we use ICD-9 code to extract people with certain type of cancer. We also try to use NLP to identify such patient. But everybody knows that there's some limitations with the ICD-9 code because it attached with certain sensitivity and positive predictive value. But NLP as a measurement tool would have the same issues. So we try to be more rigorous. We always want to validate it. And for cancer metastasis, which is often underreported in structured data, and very often to identify such cases, human manual review is warranted, but very labor-intensive and costly and time-consuming. And so we collaborate with Regenstrief, try to develop an NLP algorithm to identify such cases. So the objective of this study is to determine the value and validity of natural language processing to identify metastatic melanoma from unstructured data and compare that with the structured data query. We use the Indiana network of patient care, which is a Indiana-based EMR system created by Regenstrief Institute since 1995. It's a large EMR system with over 25,000 physicians, 106 hospitals, and 110 clinics. It currently has 6 million patients and cover inpatient, outpatient, procedure lab, pharmacy, etc. It also contains over 120 million free text clinical reports. And we also linked the IMPC data to Indiana Cancer Registry in order to test the sensitivity of our natural language processing algorithm. Okay, so this is a retrospective cross-sectional study. We include patients aged 21 years or older who have at least one clinical record in IMPC from 2005 to 2013 in two major hospitals, Eskenazi Health Foundation and IO Health. The major purpose is that because we have easy access to the medical chart in these two hospitals, and the patient identified as prisoners were excluded. The final NLP algorithm are like this. If a text report contains the strain melanoma and the derivatives of metastasis within 5-word phrases, but not categorized as negated or possible, not categorized as being the family history. The structured data definition is people who have at least one melanoma ID9 code of 172 and concurrent or subsequent secondary cancer ID9 diagnosis code of 198 or 199. So we use a Venn diagram method to compare these two to compare cases identified by NLP or structured data query. You can see the white circle represent all the cases identified by NLP, and the blue purple circle represent all the cases identified by ICD-9 codes. And there are some overlapping part, which is part B are those identified by both methods, and part A would be those identified by NLP only, and part C would be those identified by structured data only. The gold standard is for validation would be human medical chart review. As John just mentioned, we use the Regenstrief medical chart review tool. We pull a random sample for medical chart review, and I identify for the outcome are categorized as 4 possible categories, who are definitely positive, unsure but likely positive, definitely negative or unsure but clinically unlikely to be positive. In order to test the sensitivity, the IMPC network is linked to Indiana Tumor Registry, so that we identify all the registered patients with metastatic melanoma cases that have record in the IMPC system. Okay, here the result. By using the natural language processing technology, we identified a total of 1,727 metastatic melanoma cases, which include both part A and B. So 1,215 metastatic melanoma cases are identified by NLP only. Using the structured data query, we identified a total of 607 cases, and only 95 of these cases are identified by structured data query only, and 512 patients are identified by both methods. So we calculate the sensitivity and the positive predictive value for using NLP only, which includes zone both A and B. The sensitivity is 67%. The positive value when we use only the definitely yes cases as the gold standard, the PPV is 74%. When we use both, when we use the gold standard, including both definitely yes and unsure but possible, the positive predictive value increased to 80%. The structured data query by itself has a sensitivity of 35%. The positive predictive value is 83 when you use definitely yes as the gold standard, and 84 and 84% when you use both definitely yes and unsure but possible. Combine these two methods, the sensitivity is is 67%. The positive predictive value is 71% or 77%, depending on the outcome definition. So based on our finding, so the natural language processing technology identified nearly 3 times as many metastatic melanoma cases as structured data query only. The natural language processing technology has much better sensitivity than structured data query only, and the PPV of natural language processing was slightly lower than that of structured data query. But this, I think the difference is acceptable. I think the limitation of this study include that the cancer treatment was not included in the current NLP of clinical report. If we include the chemotherapy part as certain criteria for both NLP and structured data query, the result may be slightly different. And also, current finding restricted to only 1 cancer type and from 2 major hospitals, the generalizability may be limited. So I will, at the end, I would like to acknowledge my colleagues from both Regenstrief and the Merck side who helped this project. And I think this is the last slide conclude our presentation today. And John and I would be happy to answer any questions.
Wonderful. Again, thank you both very much for taking the time to present to us today. So with a few moments that we have left, we can open up the call for a short question and answer period. I'll now go ahead and unmute everyone. So if you'd like to ask either Dr. Ho or Dr. Duke anything, please just announce yourself first.
The conference has been unmuted.
This is Alec Walker.
Hi, Alec.
Can you give us a sense of why it should be that a person with malignant melanoma should have no ICD code in the record?
I think the finding is actually they do have melanoma codes, but most are missing the secondary cancer codes. That's why they are not qualified as metastatic melanoma cases by structured data query only.
I think the key piece there is that there is not a metastatic melanoma ICD-9 code, so they have to build or infer the metastatic component. That will change with ICD-10.
But wouldn't the so how did the structured data miss the cases? I would see how that would reduce the positive predictive value of the structured data, but I don't see how it would make the sensitivity so low.
I mean, why were there some patients that simply didn't have an ICD-9 code even though they had metastatic melanoma? Why didn't they have at least a plain melanoma code?
Yeah,
well, it was because they didn't have the second code. So in other words, in order for them to be considered a case, they needed to meet both having a melanoma primary code plus the secondary code. And many people did not have a secondary code, and thus they were not considered cases, and thus the sensitivity was lower.
Thank you.
But it's a good question about the vagaries of how these structured codes are used.
Well, the question really is how much we should generalize these results to other settings.
I think for cancer, it may vary case by case because cancer are very different. But I think it's in general, it's been very well recognized that the secondary cancer diagnosis code in structured data have been severely underreported.
In general, structured codes, depending on the type of thing. So for symptom-based conditions, they're typically very poor and not that sensitive. But also, you get false positives then for things like breast cancer, where people do rule out for screening purposes that end up in the database as breast cancer.
Are these cases that are being treated elsewhere and simply being mentioned in passing?
Sorry, I don't hear your question. Could you repeat that?
Are these cases that are being treated elsewhere, and so it appears only in the NLP and not in the structured data because it's just being mentioned in passing, and the care is going on somewhere else?
So that's a very good point. So, and Jinghua, maybe you can comment on whether it was an index or incident event. In many cases, you do have patients who go somewhere, they come into your catchment area, and that history is identified, but the initial diagnosis may not have been recorded. But typically with metastatic melanoma, people are sort of getting ongoing treatment. So I don't know, Jinghua, if you can comment on patients who maybe had a start where it was in a prior location and then they came into our database.
Yeah, I think the for this particular study, we do require the patient have a original melanoma cancer and then it metastasized to other sites. That's the gold standard for this study. We include that in the medical chart review part.
Thank you.
Thanks. Any other questions?
Hi, this is Bin Kai from Pfizer. And a very good presentation. Thanks to John and Jinghua. And my understanding is that your current result is based on independent query of the NLP and the structured data. And for the next step, I'm wondering if you are thinking of create some of the algorithm to use the NLP and the structured data simultaneously.
Yes, I think that's actually what we will do eventually, because when we do a study, we definitely want to mobilize all the resources we have. We don't want just give up the NLP part or give up the structured data part, but when we have them, right?
Right.
It really depends on the research question, and as you see, and I think both NLP and the structured data contribute to different aspects. Now we just talk about identifying metastatic melanoma as one condition, but in an overall study, I suppose if we want to look at a drug safety issue, we will measure hundreds of medical conditions: the exposure, the outcome, the covariate, the background patient population, their demographic, their behavior. Some of these variables would be very well documented in the structured data. Then we might do not even bother to use the NLP. But some of them, particularly those symptom-based conditions, or some life behavior or like family history, will not be routinely documented in the structured data. In those cases, we would more rely on the NLP part. So now this is just simple validation study to demonstrate the capability of NLP versus structured data. But in a overall study, when we have definitely a big study, a research project, we definitely should use both. It depends on the research question, and we do want to take the advantage of both.
I would underscore that, and it's a great suggestion. Using the combination is essentially almost always better than one or the other. We had a setting recently where we were recruiting patients with pre-diabetes for a study, and we had sort of gotten as far as we could go with the structured data. We added NLP, we significantly boosted the recruitment, but by having them both, we can really gain both the sensitivity, the specificity, and so absolutely in concert is the best performance in almost every case.
All right, thank you.
Hey, this is Huifang Liang from Takeda. So I have a stupid question, like when you do the natural language processing, so which tool do you use? So I saw your like a query in like on the slides.
Mm-hmm.
So do you use SQL?
That's a great question. So at Regenstrief, we've developed a platform that utilizes a lot of both open source components as well as custom things that we've developed and kind of have built the integrated stack. So we use our own platform that we've developed. But in terms of that technology, it's typically not SQL that's being run. It's usually a combination of something that's called Lucene, which is an Apache product combined with a UEMA or unstructured information management architecture pipeline. It relies on Hadoop for some of the distributed aspects of the query. So SQL can be used for NLP. It's just not particularly efficient. So we've developed our own platform that kind of combines the best of the different pieces.
So you develop your own tool. I could not hear you clearly because so you combined. Could you repeat that? You combined what with what? I'm sorry.
Sure. Yeah. No. Absolutely. So, and I'm happy to discuss further. And our platform is available for use outside for different contexts. But basically, it's a combination of a rapid search tool, which is based on a technology that's called Lucene, and it's combined with what is sort of a deeper dive NLP infrastructure that's called T-Tape, and some kind of custom elements that we put to glue them together, and we kind of wrap it in sort of a user interface. So it queries documents that have been basically put into file structure and then kind of decomposed into individual words to make it efficient for searching. So the technologies, if you wanted to look them up, and I think I have them on a slide here. In fact, I'll pull it up real quick just to refresh that piece. I may not have slide power anymore, but basically the technologies are Lucene, UEMA, Hadoop are the big ones.
Okay, thank you.
Great. Anyone else? Okay. Great, everyone. Thank you again for taking your time out of your schedule to join us today. We won't be holding a call in December, so the next call will be in January 2016. You'll see an invitation from us with the topic of that discussion soon. Thank you all again, and have a nice day.